This is going to be a presentation on how to prevent generator failure with real-time ground fault monitoring, utilizing Acumetrix telemetry-based technology in support of the power gen industry. So who is Acumetrix? We were founded in 1991. We're based in Latham, New York, near Albany, the capital of New York State. The original founding member of the company used to work for GE for many years in Schenectady, kind of where it all got started. So that was our history, was based in the power gen model from GE. We're a world leader in ground fault monitoring systems, primarily targeting brushless generators and motors. We utilize wireless digital telemetry systems to transmit sensor data from rotating shafts off to the stationary world. Just a little background on the Modal Shop. We are teamed up with the Modal Shop. They were founded in 1990. They're based out of Cincinnati, Ohio. Acumetrix falls underneath the Modal Shop as part of a more systems-based company that's part of the larger PCB family. So the Modal Shop is a world leader in dynamic sensor calibration systems and services. They offer many different features to support the entire power gen industry. They're designer and manufacturer of the world's most portable vibration calibrator. That seems to be the main target and the interaction between Acumetrix and the Modal Shop moving forward. Acumetrix was purchased by PCB Piezotronics in 2013. PCB was founded in 1967. They're headquartered in Depew, New York, just outside of Buffalo, about 4.5 hours from where Acumetrix is located. They're vertically integrated from machining to assembly. They have a 50,000 square foot machine center. It's very impressive. If no one has made it out there to visit that facility, I highly recommend you go out there and check it out. They're always welcoming guests. Although now with the current global situation due to COVID-19, please check ahead of time before trying to plan a trip to visit their facility. They're a world leader in sensors, industrial applications, power gen, aerospace and defense, automotive. They specialize in high temp for major turbine OEMs, primarily the dynamic pressure sensors and accelerometers. So as you can see, based on Acumetrix, the Modal Shop, and PCB, all part of the larger MTS System Sensors family, we understand power generation. We offer vibration monitoring systems, ground fault detection, proximity probe troubleshooting, combustion dynamics, industrial hygiene, slow speed vibration monitoring for hydropower. We kind of cover the whole, the whole aspect of power generation from start to finish. Somebody within our company will be able to support pretty much any question you have on your sensoring and monitoring and protection needs throughout your facility. So a little bit about me. I have a bachelor's of engineering technology. After high school, joined the military, spent 5 years there, and then utilized that through the GI Bill to kind of piecemeal my education together. Attended multiple universities to finally get my bachelor's degree in engineering. I've been with the company for over 12 years now. They've promoted me to the business development manager with an area focused on the ground fault telemetry systems and going after the end user market in North America primarily, but eventually the world as well for anything that's brushless exciter related. A little funny story about me. I was once in an ostrich relay race when I was holding on for dear life. I just put that in because it was just a funny story I could think about myself. I was a teenager, was in Africa with my family, and ended up having to sit on the back of an ostrich with no saddle and just hold on underneath the feathers of the bird in this like rodeo corral with a bunch of other people. And then they kind of released this gate, and the ostriches took off around this dirt track, and you ran a relay race with other members of your team. It was quite an experience. So definitely a memorable story of myself. So some of the markets and industries that Acumetrix serves, you can see the list here: automotive, power gen and energy, aerospace and defense, test and measurement. Obviously, this presentation is going to be focusing mostly on the power gen and energy aspect of our business, but basically anything that's rotating and companies are looking to get sensor measurements off of a rotating shaft and transmit that wirelessly, that's what we specialize in. That's our bread and butter. Specifically high-speed applications, high-temperature applications that other companies don't want to pursue. So we're very custom in nature, a slightly different business model than what PCB has, more in line with the Modal Shop in a systems-based approach to our business. Again, it's very custom. Nothing that we have is kind of off the shelf. So if a customer has a specific request, oftentimes our engineering team can meet the task to come up with a system that can reliably and accurately measure that data. So the agenda of this presentation is going to be just a kind of a quick background on generators. What is a field ground fault and how do we detect these faults? And then a little bit on the other motors and generators and solutions that we've come up with to fit into different types of machines. So most gas and steam turbines use what's called a cylindrical rotor. You can see that here. I'm going to get my little cursor available here. So these consist of this cylindrical style rotor. There's a bunch of forgings that are slotted to accommodate the turns of wire, which you can see in the copper conductors. They're about a 3 or 4 inch wide copper bus bar, copper conductor that run down into these dovetail forging grooves and form a giant turn of wire, just like a motor or generator. Same concept. There's many thousands of these turns of wire. They're insulated from themselves with thin layers of insulation, and then they're also isolated from the metal of the rotor itself with fiberglass insulation pieces inside of these grooves. So the issue of a ground fault is you don't want there to be any current flow between the high voltage, high amperage flow of electricity in these bus bars and the metal of the machine itself, the forging of the rotor. If that happens, that can be very bad. So all these materials are exposed to centrifugal force, thermal expansion and contraction. Sometimes there's stress on the copper bus bars, there's stress on the rotor itself. There's, dust gets in there, somebody dropped a screw or a washer in there. There's lots of different things that may lead to a ground fault and can cause this to degrade over time. And if that happens, again, if you have shorted turn to turns, or if you have shorts between the turns of the field windings and the forging itself, then you're going to divert your current into that and you can cause significant damage. The worst being with enough current flow, you can actually superheat this rotor to a point where it'll warp and bow, causing, as you would know, catastrophic vibration issues and cavitation and severe damage. And at that point would probably lead to replacing the entire rotor. So here's an example of a field ground fault. So basically what I was talking about, it's the insulation degradation can lead to that electrical connection between the windings themselves and the rotor forging. Traditional wisdom has always been, well, if you have one ground fault, it's not that bad because you're not diverting current through one connection. If you have a second ground fault, as the next bullet point says, 2 or more faults will then cause all of your current to divert directly into the rotor forging itself, causing this kind of damage you see over to the right where it's burned in, and it has to then go out of service and be repaired. It can lead to a lot of destruction and damage. It's not always true that 2 points of a ground fault are what customers are most concerned with. You can have a single point failure. And in the next slide, that shows an example. This is the retaining ring that covers those field windings that they come out of each side of the rotor, where you saw them all stacked up in the previous slide. And this was from a single turn-to-turn short that developed in that and caused burning into the retaining ring that needed to be repaired. Here's an example of what a generator stator may look like. Again, we're not really focusing on this because this is all stationary side of things. So that cylindrical rotor will slide down into that stator where those lights, those work lights are, causing, to be able to create that electromagnetic field as the rotor spins around at 3,600 RPM. So this is the brush rigging. There's basically two types of excitation systems for generators. You can think of the exciter as the power supply, essentially, for the generator. So the two types are brushed and brushless. So in a brushed system, which is what this picture is, all of your brush rigging and your circuitry is out in the stationary world. They bring that across with this brush rigging assembly. They bring DC power source across to that, and they contact these slip rings that are press fit onto the shaft itself. So that's how they're getting their DC power source out to the rotating shaft as the machine is spinning around. In contrast to the brushed systems, they have what's called a brushless exciter. You can think of a brushless exciter basically as an inside-out motor, or an inside-out generator, sorry. So they have the three-phase AC windings, and all of the armature and electronic circuitry and everything that is required to produce the DC field out on the rotor itself. So they have, as a result, you basically get AC currents on the rotor, three-phase AC currents on the rotor. They have to be rectified using silicone diode rectifiers to produce that DC current source that then powers the generator itself. So the challenge is, how do we get access to the rotating part of the circuitry on a brushless exciter? That's always been the challenge. So there are a few different ways that companies can do that. In the next few slides, we're going to go over that in a little more detail. So this just shows you an example of what a brushless exciter may look like. And again, is going to be the focus of this presentation, is primarily based on brushless exciters. So what are essential elements of a field ground detector on a brushless generator? It's a means of gaining access to the rotor, like I mentioned before. How do you get access to something that's rotating and spinning at 3,600 RPM, on a giant piece of machinery the size of your house? It's a means of detecting a ground fault that may occur within those field windings out on the generator itself. And then it's how you report that information or interface with the customer, with the operator. What type of data are they going to receive? So here's the kind of more traditional way to get access to the rotor. It's a slip ring approach where they press fit these slip rings. I don't know if you can see to the right where my cursor is. So one of these slip rings is connected to the steel of the machine itself, or rotor ground, and the other one would be to the negative side of the field. When I talk about the negative and positive side of the field, all that basically means is one side of the field windings versus the other. So those copper bus bars run out on the generator and form many thousands of feet of windings, and one side would be referenced to negative and the other side would be to the positive side of the field. So most classical ground detectors are connected to the negative side of the field and rotor ground. So they have these brushes that touch down, graphite brushes, I believe they are, that are powered by a solenoid. They touch down on the shaft as it's spinning, usually once per day. They inject a DC voltage that biases that negative side of the field slightly higher than rotor ground, and then it looks for current flow between the negative side of the field and rotor ground. If there is current flow, there is some circuitry that will detect if the resistance threshold is below a certain point. Usually that's set at 10K ohms. Anything below 10K ohms will trigger an alarm and let the user know you've got a ground fault. So there's no electronics out on the rotor. It's non-continuous. You obviously have the reliability limits of a mechanical connection of those brushes touching on that slip ring. They need to be replaced at least once a year, a couple times a year. We run into a lot of customers where that solenoid doesn't work anymore. It's not making a good connection, and there's no feedback to them to tell them there is or isn't a connection. You can see the sort of the receiver part of the electronics is very old. This system was probably designed and developed in the 50s or 60s. So it goes back a very long time, and there's almost no serviceability of this. Customers can't find support for this product. So the next style of ground fault detector is an optical transmission. This is just an optical IR module that mounts out on the rotating shaft. It gets its power source from the excitation of the field voltage itself. So it is continuous as long as the machine is online and running. It does have some reliability limits, of course, for an optical communication in a machine environment. If it's in a coal plant, a dirty or dusty environment, those lenses can get corroded or covered up, and obviously stops working if that happens in the case. So the next style is ours, ground fault detection using radio frequency telemetry. So ours is induction powered. So what that means is we're bringing the necessary power across the wireless air gap out to the rotor mounted transmitter that powers our electronics out on the transmitter. And in turn, it sends a data signal across that air gap back to the stationary side to let us know what the field voltage is and the field resistance out on the generator. So it's the most reliable form of data communication. It's a digital data stream that gets sent across that air gap. So it's less susceptible to EMI or RFI noise. Excuse me. And it's reliable and continuous at all times, even when the generator is off. So we'll go into a little more detail based on our technology. So here's just a basic diagram of what it works, or how it works, sorry. So it's taking some type of sensor or rotor parameter, in this case, field voltage and field resistance. It takes that information into our rotor mounted transmitter, which is an analog signal. We do some analog to digital conversion. We transmit that signal through essentially a loop of wire. There are two loops of wire, one on the rotating world, one on the stationary world, that forms that rotary transformer and creates that communication link between the rotating part and the stationary part. So data is flowing this way, and power from induction power, RF radio frequency carrier, is coming across that air gap this way. So once we digitize a signal on the rotor, we send a digital data stream across that air gap. It gets picked up in this loop of wire and then gets run to our stationary digital radio receiver, where we then do some digital to analog conversion and send the end users and power plants those signals. So they have some analog 4 to 20 current loop output signals that we provide, and also some Form C contact relays, normally open, normally closed contact relays. And we'll go into that in some more detail in the next few slides. So again, it's the link between the rotating world and the non-rotating world. Power this way, data coming back that way. So here's an example, basically modeling what a field ground fault may look like. So first we have to kind of just define it as an analytical model for a ground fault. So it's defined as some value, RL, some resistance, and some location of that field windings on the rotor. So what it is just basically looking for the potential difference of a fault-like location relative to the negative side of the field windings and rotor ground itself. So 0 is at the negative side, and 1 or 100% would be at the positive side of the field windings. We provide what's called location factor, K, and we'll go into that in more detail as we cover the process of how Acumetrix measures for a ground fault. So the classical ground fault detection method, as I was talking about before, it's a DC injection voltage that they put out onto the exciter shaft itself, and that biases that negative side of the field slightly higher than rotor ground. It looks for that current leakage to go from the field windings to rotor ground. And then there's some circuitry of a threshold that's set out there to measure, if you have current and you have voltage, you can calculate using ohm laws what the field resistance will be. And then the resistance, if it drops below a certain threshold, it'll trigger the alarm. In most cases, as I mentioned earlier, that's a single point threshold set at 10K ohms. So a good field, when it's rebuilt, rewound, it first goes into service, maybe many tens of megohms. Most utilities are only concerned with values below 500K. It's very difficult to measure any accurate resistances over 500K ohms. It just looks like a massive open wire at that point. And as long as it's very high like that, utilities aren't concerned. They're concerned with low values of resistance. So then some of the limitations of the classical method is the resistance threshold is dependent on the fault location. It's also dependent on the severity of the fault. So you would need a much more severe fault near the negative side of the field windings and a relatively minor fault near the positive side. So that could potentially lead to possible false positive ground fault results. We've had customers air their frustration on that, where they thought their detector measured a low ground fault, and they shut the machine down and did further testing, mega or pot testing, and discovered that that wasn't the case. It also only detects field resistance while the machine is running. And of course, in most cases, there are those mechanical and physical limitations from either the optical sensor or the brush rigging, slip ring assembly. So let's talk a little bit about the Ephraim system. So the Ephraim is our AT8000 series piece of equipment. That is the Earth Fault Resistance Monitor is what Ephraim stands for. So that provides continuous quantitative measurements of both the field insulation resistance and the excitation voltage. Then what we offer is the location factor, which can help determine when or where on those field windings a ground fault has occurred. And I'll explain how we do that in the next slide. We offer 2 ground fault alarm outputs, which are user adjustable. Those come set from our facility at 100K ohms and 2K ohms. So we kind of view that as a warning alarm and then a ground fault alarm. So once the resistance drops below that threshold of 100K, we will send an initial warning alarm to let the user know, you don't have a ground fault yet. However, you are trending in that direction. Time to start paying a closer look at your machine and schedule an outage so you can investigate further and get that damage repaired if needed. We also offer a malfunction alarm. Again, the 2 ground fault alarm thresholds and the malfunction alarm are those Form C contact relays, normally open, normally closed. The malfunction alarm is a normally closed contact. The reason we do that is because if the Ephraim system loses power, it will open that alarm and let them know that there is a problem with the telemetry system. We also offer 4 to 20 milliamp analog outputs, 2 channels. Channel 1 is for the field resistance, that they can trend that historical information over time. And channel 2 is the field voltage. So many utilities use that feature. They interface that into their control room, and they're looking at that 4 to 20 current loop signal. And once it falls below a certain threshold, maybe 8 milliamps, 9 milliamps, something like that, they need to start paying closer attention because they're trending towards that ground fault. We also offer digital communication options. Every system comes with its own PC software that allows you to have some historical archiving. You can trend the data through the software. It'll create a CSV drive in Excel format and will allow you to trend that data. So if you, for instance, receive that warning alarm, a lot of times we'll have the customers go down to the receiver and plug right in with their laptop and start trending that information over a whole day, so that we can take a look at that data and see it kind of moving in the right direction towards a ground fault, or wrong direction if that's what how they would see it. The Ephraim receiver also comes with optional Ethernet output. We have yet to date had a utility opt to use that feature. It would involve them getting their IT infrastructure in place. They would need a network switch, and a lot of utilities are just comfortable and used to using that current loop 4 to 20 signal, and that's what they continue to use. And we've had feedback from them that there's really no desire to move away from that going into the future, and so that's where we'll continue to offer. So a little bit of history of our global installations. Again, we offer a customized solution. So we are targeting more of a retrofit market where there are those existing ground detectors installed on these brushless exciters, and the customers have those customer pains. They have those issues with them. It's a newer technology. It's a much more precision measurement. It allows the customer to have more confidence that their machine is being protected and being monitored. We sell a lot of our systems to OEMs. They are being built and shipped around the world on new machines. So many of the big suppliers will already have an Acumetrix ground detection system installed on them. So we have some of that world-class support is 200 plus installations, 15 plus years experience of using the system. And again, we are backed by that slogan of total customer satisfaction. If the customer's not happy, we can get parts to them, get stuff replaced, whatever we need to do to keep that TCS motto moving forward. So here's a little bit of an example. What's different from the Ephraim system versus the kind of classical method is instead of injecting just that set DC pulse voltage, DC voltage, we inject a pulse that's toggled from high to low. We also connect to the positive side of the excitation field and the negative side. And as that pulse is toggled from high to low, we're doing high-speed digital two simultaneous computations of the resistance value between the negative side of the field and rotor ground and the positive side of the field and rotor ground, and transmitting that off of the shaft simultaneously. So that way it eliminates that issue where the fault needs to be much more severe at the negative side versus the positive. It basically balances that out and makes it a much more accurate measurement between those 2 points on the field windings itself. So the next few slides are going to go over some of the examples of what our system looks like. The Ephraim system comes in 2 standard styles. One is called the end of shaft, and the other one is the Midshaft. So this is an example of the end of shaft transmitter mounting system. This typically goes on smaller air-cooled units. You can see the gray transmitter is this piece that's mounted on the end of the rotor. There's a rotor end cap, which is underneath. This is all standard stuff that would already be on any smaller air-cooled unit, and we can easily adapt our transmitter right in the center line, so that eliminates any balance issues, any concerns with high-speed vibration and things like that. We mount it right to the end of the shaft, and then we install the stationary pickup antenna, which is this white ring antenna. So there are turns of wire on the ID of this white pickup antenna, and then on the OD of this gray transmitter snout. And that is what makes that connection to form the rotary transformer between the rotating world and the stationary world. And we transmit that across approximately a 3/8 to 1/2 inch air gap. And then we're bringing power back the other way to power all of our electronics out on the motor. So you don't need any battery or power source out on the rotor itself. Everything comes from the stationary side, and that digital data comes back and runs off to our receiver. To the right, you can see this is an example of a customer mounting our receiver on some unistrut. That's usually we would recommend that they do that. That would be something that the end user would be responsible for. They would take care of the installation of our equipment. We would send this out ahead of time before their scheduled outage, and a lot of this stuff can get done and mounted before we show up to do the installation and commissioning of the rotor mounted components. There's only one link that needs to go between our receiver and the pickup antenna, and it's just this coaxial cable. So again, that's a fairly simple installation from their end. And then the end user would be responsible for any of the outputs that have to run off to their control room to interface the Ephraim system to their operators. So here's just some more examples of our Ephraim receiver. We offered a cooled option. This is used in many areas such as the Middle East or the Southwest or the Southeast of the United States, where the environment is very hot. Ambient temperatures can easily exceed, 100 or 120 degrees F. Our Ephraim receiver electronics are rated at 50 degrees C, so that's approximately 122 F. So with the addition of the cooler, they're allowed to operate, I believe it's another 20 degrees F above that, and gives them that assurance that the sensitive electronics are going to be protected over time. To the right, just another example of a non-cooled version and what it may look like installed at a utility. This customer chose to mount this just directly to the concrete bulkhead right below the exciter doghouse. And then they supplied the conduit that ran our coaxial cable up about 80 feet above to the exciter doghouse, and then all the outputs from our system running the other conduits off to the control room. So pretty standard stuff on how we would see our system installed at a power facility. Excuse me. So here's a kind of more of a close-up of the receiver, the digital computer interfaces that we offer, as well as the relay contacts and the analog outputs. So in order to set up the Ephraim system on site during the install and commissioning, you would have to connect a USB to serial port cable to the RS-232 connection. That connects right to a laptop easily, where you've installed the Ephraim View software, and that allows the user to adjust those field resistance thresholds of the warning and ground fault alarm, as well as change the speed at which that data transmission happens between transmitter and pickup. You can adjust that. We usually recommend that customers leave that transmission data rate at about 10 seconds or more, just to eliminate any kind of like false positive readings. There's really no need that you need a faster measurement than about 10 seconds, because this is not gonna be something quick. This is a long-term monitoring feature that they're looking at that field resistance for a year or 2 years at a time. Up in the top right is the AC or DC power input into our electronics. As long as that power is brought into our receiver, the telemetry system is going to be functioning, and that is why, and these orange blocks here are the Form C contact relays, and that's why that first one, the malfunction alarm, is that normally closed contact, so that if there is loss of power or any interruption in that, it'll trip that it'll open that normally closed contact, allowing the user to know there's an issue with the telemetry system. The next two orange blocks are alarm 2 and alarm 1, the warning and ground fault alarm. And then there's just some other terminal block interfaces for the analog 4 to 20 current loop outputs. And then over at the bottom left corner, this is the a Rabbit microcontroller board that houses the software, Ephraim View software, and also offers that Ethernet connection via RJ45. But again, we haven't had any utilities opt to use that feature since I've been with the company. So here's an example of what the Ephraim View software would look like. It offers them a graph of what the resistance trend plot will look like over time. It's going to appear as sort of this scatter, because again, it's not able to measure accurately any resistance values over that 500 k ohm. It's just going to look like a massive open circuit. So it's kind of toggling between, in this case, it looks about 10 meg ohm and 100 meg ohm. When this resistance starts to drop down and gets below that 500 k value range, it'll become a a much more linear plot that you'll see that graphic interface really start to show the resistance more accurately. So again, the customer should not have any concerns. This would be a healthy rotor. This is what we would normally expect to see, that scatter pattern up above, at least 1 megohm. Usually, like I said, on a good rotor, it's that 10 to 80 megohm range. So the user can then adjust some of the thresholds down the bottom right corner. There's an access code, and this is detailed in the manual that every system would get. The access code is the same for every Ephraim system. It's Tesla ! And then that'll allow you to go into the setup and change those field resistance threshold values. Some users like to keep that a little closer together. So instead of 100K and 2K, they may opt for something like 60K and 20K. Again, that's totally customizable to each plant and how they choose to interface to that output. Then we have on the right-hand side, you can see the disk archiving setup that allows the user to start archiving the data, and it will export that to Microsoft Excel .csv drive, and they can look at that data over a much longer period of time. Again, we would probably suggest they do that once that initial ground fault alarm, that warning alarm comes in. They don't need to do that all the time. That's what they're utilizing, that 4 to 20 current loop output. That's the trending feature that they're most concerned with monitoring. So why would utilities consider upgrading to the Aphrom system? We've harped on this quite a bit, but it's really just the poor reliability. It's very hard to get serviceable items from these old ground detection systems. They've been in service for 60 or 70 years. They have a very high impact failure, and that doesn't give them that confidence that their machine's being monitored properly. So what a lot of utilities will do in that case is they'll schedule sort of unnecessary outages just to check and make sure they don't have a ground fault and turn the unit off. And when you're off and not creating energy, you're losing money, and that's something that they don't like. So our trending information and our ability to more accurately measure the field resistance gives them that peace of mind that they're going to be monitored much more accurately than traditional systems that are out there. So here's an example. We covered the first part was the end of shaft Ephraim system. This is a example of what an exciter may look like on a much larger, typically hydrogen cooled machine. To the right where this wood covering is the PMG, or permanent magnet generator, for the exciter. There's some cooling fans. There's an exciter bearing. And then in here is all the armature and circuitry for the brushless exciter. Then there's the diode rectification wheels, one for the negative side and one for the positive side of the field. And then it goes down more the exciter shaft to this coupling flange all the way over to the left-hand side. And this is where the exciter will then couple to the generator itself. So this is typically where we would plan on mounting our next style of Ephraim system, which is that Midshaft style, and we'll go into more detail in the next few slides. So here's an example of the Midshaft Ephraim transmitter. It's a two-piece split collar design that has an electronic module on one half, and then a weighted dummy module on the other half that weighs the exact same as the electronic module. It's connected across this half joint here with high strength Umbraco bolts is how we make that contact, and it's torqued down to each shaft dependent. There's a specific torque rating that will be in every manual dependent on the size of the shaft as well as the speed of the machine itself. As I mentioned earlier, in North America, most power generation machines rotate at 3,600 RPM. Some of the larger machines are 1,800 RPM. So again, speed and diameter are those two critical components that we're going to need in order to accurately design this midshaft solution to their specific to their exciter. Here's a close-up of how we make that half joint of the collar. Again, it's high strength bolt that goes through and gets bolted down across that half joint. And then we also provide a locking set screw as another mechanical feature, just to give you or the end user that extra peace of mind that that bolt could never come loose or work its way out. This is the electronic module that's embedded in the steel collar itself. We have to make connection to rotor ground. So as I was explaining before, the process to accurately measure for the field resistance and field voltage, we have to make contact to the negative side and the positive side of the field, as well as rotor ground. So we use the steel collar itself to get that rotor ground connection. So that has to get mounted directly to the shaft, a very tight fitting application, so that that's a reliable electronic ground connection. And then on the other side is where the positive and negative leads run off onto the board itself and make that contact. And we'll go into a little more detail on that. So here's a typical mid-shaft installation, what it may look like. So again, this is the coupling flange that is going to mate up to the generator, which would be off to the left, which would have an identical coupling flange that they then get all bolted together. So you have to be able to get the electronic bus connection, the negative and positive side of the field, from the exciter over to the generator. And this is how they decouple it from that. And I'll show you in the next few slides how they get that electrical connection. So this is the end view of what the rotor has, and the exciter will have the exact same coupling, just like this. So those field voltage connections and the plus and minus are run through the bore of the rotor itself and the exciter rotor as well, and they're broken out into what's called this butterfly leaf assembly. So one of these copper bus bars will be the negative side and one will be the positive side. They're isolated from the rotor by typically it's G10 or G11 fiberglass material, and then as well from themselves or from each other with another piece of insulation material. So this one on the right is a cross-sectional view of how we make that connection. So inside that coupling flange bore is how they bolt together the two butterfly leaves that match up. And we just drill and tap a 1/4-20 stainless steel threaded rod right into one of those large hex head bolts. And we run our threaded rod right through that coupling flange bore directly into our rotor mounted transmitter. So that would be your plus and your minus field voltage connection. It's a very reliable way of getting access to that electrical connection, and is as least invasive as possible for the end users. They really don't have to modify any part of their machine except for that drilling and tapping of the two bolts where that contact is made. So that's an example of the butterfly leaf field voltage contact. We then will cover our stainless steel threaded rod in this fiberglass material to prevent any risk of voltage breakover to the coupling flange bore itself, which would obviously be field ground or metal steel of the machine. So these pieces will offer strength and will be a tight fit inside that bore to prevent any bending or warping of our threaded rod. And then the more narrow pieces are just covering it and to prevent the isolation from voltage break. And then it just gets threaded in with this pipe thread piece on the end. And that shows an example of how we install that into the coupling flange on the larger. Again, this is for the larger, typically hydrogen cooled Westinghouse machines is how we do the connection for the negative and positive side of the field. We then will coat the threads with a special, this looks like Teflon tape. We've since gone to a special epoxy that has PTFE material embedded in it that we will coat those threads. And then we provide a seal washer on the end of the of this pipe thread piece to protect against any risk of hydrogen leak that comes out of that bore. We were approached by one of our OEMs many years ago that there was a very, very small chance that hydrogen could leak out So we've gone the extra steps to prevent any of that. And we've actually had this whole assembly tested by a company, and it's able to withstand up to 20 PSI of gas leak pressure. And the spec was only to prevent 10 PSI. So it's more than capable of preventing any risk of leak of hydrogen into the exciter. This shows the collar mounted to the steel of the rotor itself. Again, we need the utilities to have this a good clean surface for us to mount, because this is how we're picking up that electrical ground connection. So this is, they've done a very good job here. They probably removed a little more paint than what would probably be necessary. We usually just need it right underneath where our steel has to bolt to the shaft itself. But this was a customer that did a very nice job for us. So that was an example of the larger hydrogen cooled machines. Here's an example of what the exciter may look like, again, for that end of shaft system on the smaller air cooled units. This is the other retrofit option that we have that's a little more detailed than the first pictures I showed. So these are the diode rectifier wheels. You can kind of see in here where these heat sinks are. Underneath there are 2 parallel diodes. They do parallel for redundancy. If one dies, the other one can still do that rectification. There's going to be a positive wheel and a negative wheel behind it. And this red piece is what's called the rotor end cap. So this is all what would normally be on a smaller air-cooled unit. This is very typical to what we would see. So we came up with the concept of, why can't we just mount our transmitter right to the end of the shaft and just have them modify this rotor end cap by putting a small hole in the center of the end cap. And so that's the style that we do for many of our end of shaft systems. So here's an example of the rotor end cap that's been machined and modified with a hole in the center. We then can run wires down to the bus bars, which are underneath this. So one side would be positive and the other side is the negative side of the field. Then we provide an aluminum adapter plate that picks up the existing holes that are already in the rotor end cap. So again, the customer doesn't need to machine or drill and tap any holes for that. We try to design everything so that it can pick up what's already there and make it as easy as possible for them to retrofit this equipment into their generator. And then once that aluminum adapter plate is installed, we can mount our rotor mounted transmitter, which is this gray piece, picks up this 4-bolt pattern right to the adapter plate. Once the transmitter is successfully mounted and we connect the negative and positive side of the field and rotor ground, we then can install the stationary components, which are this G10 fiberglass tube piece, which we call the top hat assembly. Over to the right, you can probably see why we call it that. That has some T80 material that we allow the stationary pickup to be adjustable axially, so we can slide this pickup in and out and align it to where we see fit. The idea is you want to align it slightly axially towards us in this picture, so that way you allow for the rotor growth. When the machine is running for a day or two, it'll reach thermal equilibrium and will actually grow and push that rotor mount transmitter towards us. So having this setup allows us to adjust that to a range that's going to be the most optimal. Our equipment will operate at a fairly good range. It's typically plus or minus an inch. So even if this stationary component is misaligned up to 1 inch, towards us or further in the Z direction, if you will, that'll still operate. But we obviously want to install this equipment and commission it to the most ideal setting possible. And then once that's all done, we put a plate cover piece over that, and then that just gets connected to a flexible conduit where we have that BNC cable run off to our stationary receiver. So again, why switch to ground fault Ephraim system? Customizable, that's really the biggest thing. That's the thing we're trying to push most in this presentation, is that we offer that ability to retrofit existing many different types of generators and exciters that are out there that may or may not have a ground detection system on them. So that's really the market that we go after, is competing with other companies that already have a system, and we're replacing it with something much better and much more accurate. It gives you that continuous monitoring at all times of the generator. Some of the advantages are that ability to trend that data over time, so they can monitor for that breakdown. On their traditional systems, it's literally just a go, no go. You know, that old brush actuator style, they may contact and take a measurement one day and it's fine. The next day you come in, you've got a ground fault. You have no sense of predictability of knowing when that may occur. Do you know if you're at 15K ohms one morning and you're very close to that 10K threshold, and you come in the next day and all of a sudden you've got a ground fault and everybody starts panicking, shut the unit down, and you know, get some repair done. So that's the biggest advantage, is just that ability to monitor it over time. Reliable, long-term, healthier machine. Cost savings, I really can't stress that enough. You know, avoiding those unplanned outages can cost utilities, you know, many millions of dollars. If they have a forced outage and they're not planning for it, and if they're one of these smaller plants, a lot of times, not only are they down and not producing energy, but they have to buy energy from a competitor to support their portion of the grid. And as you can imagine, a competitor is not going to be selling you power at a very cheap rate. So I just wanted to kind of summarize this with some of our future webinars that we're going to be having in our 2020 series. Up next, it's going to be on December 10th, the human vibration measurements, risk limits, and mitigation. And then on December 17th, it's why calibrate, the importance of accelerometer and pressure sensor calibration. So thank you again for your time. I really appreciate it. Thank you.